The 1990s marked a turning point for artificial intelligence, a decade when the field began to recover from the setbacks of the AI winter. What sparked this resurgence was not a return to the symbolic AI approaches of the past, but the rise of something entirely different: machine learning. Instead of programming systems with rigid rules, researchers began teaching machines to learn directly from data. This fundamental shift not only revived AI research, but set the stage for the transformative applications we rely on today. To understand why machine learning emerged, we need to revisit the challenges that had stymied earlier AI efforts. Symbolic AI, for all its theoretical elegance, depended on predefined rules and knowledge bases painstakingly crafted by humans. This approach worked well for structured tasks like solving puzzles or playing games, but it fell apart in the face of real-world complexity. The dream of creating truly intelligent systems required something more: an ability to adapt, learn, and improve over time. Enter machine learning. Rather than relying on explicit programming, machine learning allowed systems to infer patterns and relationships directly from data. This approach was revolutionary, but it also required significant computational resources and access to large data sets. Fortunately, the 1990s provided both. The first key enabler of machine learning was the dramatic increase in computing power. By the early 1990s, computers were faster and more affordable than ever before. Tasks that would have been infeasible just a decade earlier could now be tackled in hours or minutes. This leap in processing power opened the door for more ambitious experiments with machine learning algorithms. The second enabler was the explosion of digital data. As businesses and governments digitized their records, researchers gained access to vast amounts of information, raw material for training machine learning models. Meanwhile, the growing popularity of the internet provided a treasure trove of text, images, and user interactions, further expanding the possibilities for data-driven AI. The third enabler was the rediscovery of neural networks. Neural networks had been proposed decades earlier, but fell out of favor during the AI winter due to their computational complexity and lack of practical success. However, by the 1990s, researchers like Geoffrey Hinton and Yann LeCun were refining neural network algorithms and developing new techniques for training them. One of the most important breakthroughs was backpropagation, an efficient method for adjusting the weights of a neural network to minimize errors. This advance breathed new life into the connectionist approach and laid the foundation for deep learning. As these pieces came together, machine learning began to demonstrate its potential. One of the decade's most high-profile successes was IBM's Deep Blue, the chess-playing computer that defeated world champion Garry Kasparov in 1997. While Deep Blue relied on a combination of brute force computation and domain-specific programming rather than machine learning in its modern sense, it symbolized the growing capability of AI systems to handle complex strategic tasks. Behind the scenes, researchers were making quieter but equally significant progress. Algorithms like supervised learning gained traction, offering a structured way to train models using labeled datasets. For example, a supervised learning system trained on emails labeled as spam or not spam could learn to classify new emails automatically. This approach proved effective across a wide range of applications, from fraud detection to image recognition. While supervised learning became a cornerstone of machine learning, other techniques also emerged to tackle different challenges. One particularly influential approach was support vector machines, or SVMs. These algorithms excelled at classification tasks, especially in high-dimensional spaces, where data had many variables. For example, SVMs could analyze data points with dozens or even hundreds of features and find the optimal boundary to separate categories, such as distinguishing between fraudulent and legitimate transactions. Their flexibility and accuracy made them a popular choice in the 1990s for researchers and industry professionals alike. Machine learning's impact during this time wasn't limited to academic labs. Practical applications were beginning to emerge and demonstrating its value in solving real-world problems. In image recognition, researchers developed algorithms that could classify images based on patterns in their pixel data. These early systems were primitive by today's standards, but they set the stage for the advanced computer vision technologies we now take for granted. Speech recognition was another area of rapid development. Companies like IBM and AT&T worked on systems that could transcribe spoken language into text. Unlike earlier rule-based approaches, these new systems used machine learning to analyze large data sets of recorded speech, allowing them to adapt to variations in accents, speed, and pronunciation. While still far from perfect, these systems represented a significant step forward, making speech recognition more accessible and practical. In the financial sector, machine learning began to prove its worth in risk assessment and predictive modeling. Banks and investment firms used algorithms to analyze historical data, identify patterns, and make informed decisions about loans, investments, and fraud detection. These applications highlighted one of machine learning's greatest strengths: its ability to uncover insights that might be missed by human analysts, especially in large, complex data sets. But machine learning's rise was not without its challenges. Overfitting, when a model performs well on its training data but fails to generalize to new, unseen data, was a persistent problem. Researchers developed methods like cross-validation and regularization to address this issue, ensuring that models remained robust and adaptable. These techniques became essential tools for building reliable machine learning systems. Another challenge was the so-called black box nature of many machine learning models. Unlike symbolic AI, which relied on explicit, understandable rules, machine learning models often operated in ways that were difficult to interpret. This lack of transparency raised concerns, particularly in high-stakes applications like healthcare and finance, where understanding the reasoning behind a decision was crucial. Despite these concerns, the benefits of machine learning often outweighed its limitations, driving continued investment and research. By the late 1990s, machine learning was no longer a fringe area of AI. It was becoming the central focus of the field. Companies like Microsoft and Google, which were emerging as tech leaders, began incorporating machine learning into their products and services. The groundwork laid during this decade would eventually lead to the explosion of AI applications in the 21st century. Looking back, the 1990s were a transformative era for artificial intelligence. The shift from symbolic reasoning to data-driven learning wasn't just a technical evolution, it was a philosophical one. Researchers began to see intelligence not as a set of predefined rules, but as an emergent property of systems that could learn and adapt. This new perspective paved the way for the breakthroughs we see today in areas like natural language processing, computer vision, and autonomous systems. The rise of machine learning in the 1990s reminds us of the importance of perseverance and adaptation in the face of challenges. It was a time of rediscovery, reinvention, and relentless curiosity, a reminder that even when progress seems slow, the seeds of transformation are always being planted.